Good day. In this lecture, we will discuss the types of crystals, focusing on how bonding determines their properties and applications. By the end of this lecture, you should be able to differentiate crystal types based on their physical properties and applications. Ionic crystals are held together by electrostatic or Coulombic attraction between oppositely charged ions, and this strong interaction gives them high melting points and rigid structures. For covalent network crystals, atoms are connected by continuous covalent bonds in a three-dimensional network. Examples include diamond and quartz, and these are extremely strong and rigid structures. In covalent molecular crystals, lattice points are occupied by molecules. The forces between them are either a van der Waals force or a hydrogen bonding. These are much weaker than ionic and covalent bonds. The last type of crystals that we have are metallic crystals, and their atoms are held together by metallic bonding where electrons are delocalized. This allows for good electrical conductivity and flexibility in structure. Each crystal type differs in cohesive forces, mechanical strength, melting point, and conductivity. Understanding this relationship is critical for predicting material behavior. Ionic crystals are hard and brittle. They have high melting points and are poor conductors in solid form. Examples include sodium chloride and magnesium oxide. For covalent network crystals, they are extremely hard, they have very high melting points, and are poor conductors of electricity. An exception of that is graphite, which conducts electricity due to its layered structure. For covalent molecular crystals, they are soft, they have low melting points, and they are poor conductors of electricity. Examples include carbon dioxide, iodine, and sugar. Metallic crystals have variable hardness, good electrical and thermal conductivity, and malleability. Examples include sodium, magnesium, iron, and copper. The key principle is the type of bonding determines the properties of the crystal. Strong bonding leads to high melting points and rigidity, while weak intermolecular forces lead to softness and low melting points. Now, for liquid crystals, they are a unique state of matter. They have properties of both liquids, meaning that they can flow, and crystals, meaning they have some degree of order. Liquid crystals are classified into thermotropic, dependent on the temperature, lyotropic, dependent on temperature and concentration, and metallotropic, dependent on composition and structure. For thermotropic crystals and lyotropic crystals, they are mostly organic molecules, but for metallotropic crystals, they are both organic and inorganic molecules. These materials are important in applications such as display technologies and advanced materials. They demonstrate that structure and order can exist even in partially fluid systems. That concludes the lecture on the types of crystals. Focus on how bonding type determines physical properties as this is the key to understanding material behavior.